Hey y'all, it's Mr. Boy and I'm back at it again, and today it's time to talk about some discrete random variables. Now, discrete is just the opposite of continuous, so don't get worried about the word discrete here, and random variables is just telling there's an event that happens randomly. So maybe what we should do is get the definition and get it into some examples. So definition-wise, a random variable is just some measurable quantity that takes on a value or some range of values, and we denote a single event as x. So notice, the single event is lowercase, and then a capital letter is the entire thing, like sort of the sample space. Okay, let's do an example so it makes sense, because there's no point getting bogged down in the language of it. Okay, and here's our first example. Imagine that we throw a fair coin, meaning that it's a 50-50, heads, tails. We throw it 4 times, and we count the number of times that we get tails. We're going to let capital X be the number of times that we get tails, so that's our count, and then we're going to express the probability in this way. So what we're going to do, we're going to make a tree diagram to review that. We'll lead into a discrete random variable table of the probability, and then we'll make a histogram as well. So let's do it. So if we're going to flip a fair coin 4 times, that's actually 4 distinct events. So on the first one, you might get heads, and you might get tails. And there's a 1/2 probability of heads and a 1/2 probability of getting tails. That's flip 1. What about flip 2? On flip 2, you might get heads, you might get tails, and if you got tails, you might get heads the next time, and if you got tails, you might get tails again. Each of those has a 1/2 probability. And flip 3, you probably get the pattern by now. On flip 3, you might get heads, or you might get tails. And if you went heads, tails, you might get heads or tails, and you might get heads or tails. And each of those has a probability of 1/2. Now, guys, I'm going to stop the video here. It's going to jump right to the end of the table, so you don't have to watch me write these for the next 30 seconds. Now that the table is done, let's consider how many possible outcomes there are, how many possible different things there are that can happen. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different events. So our sample space contains 16 events. What we're going to do now is we're going to make a discrete random variable table of those probabilities. So yes, there are 16 different ways to get different outcomes. However, what we need to remember is that the random variable here is the number of times we get tails. And so what we're going to think about then is how many different times can we get tails. The table's going to look like this. That's a capital X and a lowercase. And then what are all the different things that can happen? So in terms of number of tails, we could get 0 tails, 1 tails, 2 tails, 3 tails, or we could get all 4. That's a possibility. So this is what our table looks like. Now, we noted that there are 16 different outcomes. That makes sense. That's actually 2 to the 4th power, and this is a 1 out of 2, 4 times, so 2 to the 4th power is the number of events that could possibly happen. Now we ask, how many ways could we get no tails? Well, no tails would be all heads, so this is the only branch that has that, so that's 1 out of 16. What about this one? This is down here saying how many different ways, or what's the probability of getting all 4 tails? Tails, 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 tails. There's only one way for that to happen, so that's 1 out of 16. Now we're going to consider all the different ways, and I'm going to color code this. What are all the different ways that we could get exactly 1 tails? So we could get tails, heads, heads, heads. That's a possibility. Or we could get heads, tails, heads, heads. Or we could go heads, 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 tails, heads. That would be exactly 1 tails. Or we go heads, 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 tails. And so that would give us 4 out of 16. Then we're going to ask how many different ways could we get 3 tails. So that would be tails, 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 heads. That would be one way. Or tails, tails, heads, tails. That would be another way. Or we could go tails, heads, tails, tails. Are there any others? We could go tails, nope, that's tails, heads, heads, tails. That's 2 of them. We could go heads, tails, tails, tails. That would be another. So there are 4 out of 16 ways that we can get 3 tails. And what we're going to remember is that the sum of all probabilities has to be 1. So there's 5 out of 16 here and 5 out of 16 there, which means we've already accounted for 10 out of 16. Which means that the complement of that is 6 out of 16. So there's 6 different ways that we've not accounted for in which we could get 2 tails. So that is the discrete random variable table of probability. And then we'll look at a histogram on the expected distributions. So all that is we're going to take this same table and we're going to make a histogram out of it. So there along the bottom, I better scroll down a little bit. So we're going to have the outcomes, and the outcomes are 0 tails, 1 tails, 2 tails, 3 tails, and 4. Vertically, we're going to have our probability, and that's going to go up as high as, in this case, we're just going to go 1, 2, 3, 4, 5, and 6. And that 6 represents 6/16. And now we can put in these different bars in our histogram. So 1 out of 16 is our first one. And then we have 4 out of 16 corresponds to 1, so it jumps up to 4. And then for 2 tails, it goes up to 6. For 3 tails, it goes back down to 4. And then back to 1. So we have a roughly bell-shaped and symmetric distribution here. Okay, so guys, that's the basic concept of a discrete random variable. It's just some event, and it can have any range of values. In this case, there are 5 different ways for it to happen: 0, 1, 2, 3, 4, or 0, 1, 2, 3, and 4, excuse me. And this is the type of table that we normally use. Let's look at another example. In this one, we're going to be drawing marbles from a box. So 2 marbles are selected at random, and in that we have 6 green and 2 red marbles. We're going to let x equal the number of red marbles. Okay, we're discussing red marbles in this question. We're going to make a table to show the sample space and the probability of each possibility. So we're talking about red marbles. What are all the different numbers of red marbles we could possibly draw? We could get 0, that'd be all green. We could get 1, that'd be a red and a green. Or we could get 2, that would be both reds. So we can make our table. So the outcomes of 0, 1, and 2, and maybe I'll make a note, I'll circle this in red so we know that we're talking about the number of reds. And then down here we'll have to include our probability. So the probability that the random variable achieves each of those x values. Alright, so here we go. 2 marbles selected at random, and let's do this first. Let's find the probability of getting no red marbles. So what that would mean is you reach in, and the first marble you get is not red, meaning it's green. So I'm going to show that this is our calculation for x equals 0 over here, our probability for x equals 0. So if you got a green marble, that would be a 6 out of 8 likelihood of the first one being green, or of it not being red. And then what's the probability on the next one? Well, since you already have one in your hand, that's going to be 5 out of the 7 remaining are still green. So what we'll do, we'll multiply those together. 6 out of 8 simplifies to 3/4, so that's 3/4 times 5/7. So that is 15 out of 28. Now let's go down here. Now guys, notice in both examples, I've kind of avoided the middle one. Typically, there's more different ways that the middle values can be achieved, and it's a more difficult calculation. So typically, if we start from the ends and work our way in, it's a little bit easier. So let's go down here. If we have 2 red marbles. Now, there were only 2 marbles in there to begin with. So what was the probability that your first marble was red? Well, 2 out of 8 are red, so that's that probability. And then what's the probability that your next marble is also red? Well, there's only 1 red left out of a total of 7. So that's going to be I should have had parentheses around these as well, y'all. So that's our probability of getting 2 red marbles, or of getting both red marbles, I should say. And that looks like that is, well, that's 1/4 times a 7th. So that is 1 out of 28. And so that's 1 out of 28. We remember that all of the possibilities have to have a total probability sum of 1. And so we have 16 out of 28 represented here already. And so what's left? That would be 12 out of 28. And yeah, I get that that simplifies, but I like leaving it like this so I can see that those 3 sum up to 1. So make a table to show the sample space and probability of each possibility. Check. This is it. We're done. Here's an unrelated example that I'd actually like you to pause the video and try just to make sure you have this concept. If you don't have this concept down yet, then of course the video hasn't made sense. So let's double check. Here's what it was. You have to understand that the sample space has to have a total probability of 1s. If you have a 0.53 and a 0.3 there, those add up to 0.8, which means this value must have been 0.2. And that's all the concept is. Now let's talk about statistical expectation. Now, guys, when we say expectation, this doesn't mean like, oh, I expect it to rain on Friday because it hasn't rained in a while. It's not that. It's like literal, it's a statistical calculation. And the best way to understand it, it's the long run average of repetition of a given event or an experiment, or an action. So like if I do this over and over and over and over again, in the long run, what do I expect that all those results to average out to be? So let's do an example with a lottery. In this lottery game, we have a $4 million jackpot, and each ticket costs $2. 6 million people are going to play, and exactly one of them is going to win. We want the expected value of a ticket. What we might need to do first is talk about this formula up here. The first part, all that says is the expectation of the variable, like literally the expectation of the variable. This here is saying we need to add up. X is each outcome, or each event, and its probability. So for this example that we're going to do, let's consider the sample space. If you buy a lottery ticket, what are all the possible things that can happen? You could win, or you could lose. So based on that, we now know what the two outcomes are. We know like the concept of the outcomes. We'll have to do them numerically. So we know those, and we can find their probabilities. Let's talk first about what happens if you win. If you win, the jackpot is $4 million. You don't actually get $4 million. Well, you get $4 million, but we have to also take into account the fact that you spent $2. So this is actually 4 million minus 2 is the outcome. What's the outcome if you lose? The outcome if you lose, and we're talking about this right here, the outcome is that you lose $2. Now we need to multiply each of those by their respective probabilities. In this question, what's the probability that you win? Well, they said 6 million people play, and exactly one will win. So you have a 1 in 6 million chance of winning. Which means, what's your probability of losing? Well, it has to be the complement of that. These probabilities have to add up to 1 because that's the entire sample space. Which means you have a 5,999,999 shot out of 6 million of losing. Now, we're going to type these in a calculator, and notice I've put a plus sign in between because that's saying to sum up all the outcomes. When I type that all in my calculator, I get negative 1.33, and in this case, it's dollars. Now, some people say, but wait a minute, Mr. Boyd, and that doesn't make sense because there's no way to lose $1.33 in this context. That's true. What's happening is, most often, you're going to lose $2. But the expected value isn't losing $2. The expected value is, on average, losing $1.33 because once out of every 6 million times, you win almost $4 million. Okay, so that's saying, like, if you played this game, let's say 100 million times, in the end, you would have, on average, lost about $1.33 or $1.33 for each time that you played. What that tells us is that this is a losing game. This is a game where you as a player, you have a reason to believe that you're going to lose money. And so what we would want to maybe think about is, particularly, people will say they're investing in the lottery. This doesn't meet the definition of an investment. An investment has to have an expected value that's positive. So you can't invest in the lottery by nature of the fact that it has this negative expected value. Let's see another example. Here's another game that I just made up just for fun. Here's a game where you play 75 cents every time you play. In the game, you flip a coin, and if you get heads, you get $2. But if tails comes up, you give $1 to the dealer. We want to know if this game is a good financial investment, and that's asking about the statistical expectation. A good financial investment would mean that it has a positive statistical expectation. So similarly to the last game, and if you want to pause the video and try it, that'd be awesome. I think you probably can get it. We have two outcomes. We could win or we could lose. We have to consider, in the winning case, how much do we really win? Yeah, we get $2, but not really, because you don't get refunded this 75 cents. So yes, you're going to be handed $2, but it's $2 minus the 75 cents you paid in. So you really only get $1.25 when you win. And that's really, really sneaky, y'all. That's a way that sometimes, like, casinos will try to get you. They'll make it feel like you've won all this money, but you're not feeling that you've paid in that same transaction. Okay, so what's the probability of that? That is, well, it's just a coin flip. So probability of 1/2. Probability of losing, also 1/2. What do you lose if you lose? If you lose, you give $1 to the dealer, but you don't get back that 75 cents either. So it's actually negative $1.75, because when you lose that 75 cents you paid to play, and you also lose that dollar. So now we can type this in the calculator and we can see what we get. And it turns out this game has a statistical expectation of negative 25 cents. So is this game a good financial investment? No, absolutely not. So what game does have a positive financial, or what game is a good financial investment? What game does have a positive statistical expectation? Well, probably no game that anybody's ever going to ask you to play, because why would someone ask you to play a game where you have the advantage? Usually these games of chance that we talk about start where either it's a 50-50 or where you have a statistical disadvantage. Now this one's interesting because the probability of winning and losing, they're the same. However, based on the cost structure of the game, you have a disadvantage in this game. So unless you just really love paying 25 cents to play games, this is not one that I would recommend that you play. Now we're going to look at some typical textbook or some test style questions. These ones are going to be outside of context. So we did the contextual examples first so we could get the processes down, and now we can probably answer these questions. So in this case, we have a random variable x. It takes on values of 1, 2, and 3. 3 is twice as likely as 1 or 2, and 1 and 2 are equally likely. We need to find the expectation of x. So this is exactly what we've done so far in the lesson today. What I want to do for this is I actually want to make a table so I can organize my thinking. And I'm going to do this in a way that's guaranteed to get the right answer no matter how hard the question is. I'm guessing that if you pause the video and think about it, you can actually figure out these probabilities in your head. But I'm going to show you the surefire way to always get it right. They told us that 3 is twice as likely as 1 or 2, and 1 or 2 are equally likely. So if 1 and 2 are equally likely, and 3 is twice as likely, we could write out their probabilities like this. And what that would then tell us, since we know all of these have to sum up to 1, we add those up, that would say 4p equals 1, so p equals 1/4. That allows me to come back in here and actually plug in the number. So p is 1/4, which means that, and I'm going to write it, well, I'll write it as 1/4, why not? So 1/4, 1/4, and if 3 is twice as likely, that's 1/2, and we can verify those do add up to 1. I know the question didn't ask for that, but it sure is going to make this easier. Because now we remember that when we're finding the expectation, all we do is take each outcome and we multiply it by its probability. So the calculation looks like this. So for the expectation of x, I'm going to take the first outcome, which is 1, and multiply it by its probability of 1/4. And then I take the next one, 2, and I multiply it by its probability of 1/4. And I take the last outcome, 3, and I multiply it by its probability of 1/2. And we just simplify that out now. So that says 1/4 plus 2/4 plus 3/2, which, you know what? I'm going to rewrite 3/2 as 6/4, so that we have a common denominator, and I can add all those together, and I get, whoops, except I made a mistake. And 6 plus 2 is 8, plus 1 is 9, so we get 9/4 is the statistical expectation. So guys, that's all it is. You're multiplying these together, multiplying these together, multiplying these together, add all those results up. That's all it is. And this will be our final example of the day, and this really is a test style question. So here we have one where a probability distribution is given by a formula, and we're told that x is 1, 2, 3, and 4. So we're going to start the same way we started the last question. We're going to start by listing out our outcomes and their probabilities. So the outcomes are 1, 2, 3, and 4 as listed right here. And then we're going to have the probabilities for each of those, which we don't actually know yet. And this should be a capital, so sorry about that. So here's what I do know, though. I was given a formula right here that tells me how to figure out the probabilities of each event. So what they say to do is they say you take x and you divide that by k. And for each of these, we know what x is. For the first one, I plug in a 1, so I get 1 over k. For the next one, I plug in a 2, 2 over k. Next one is 3 over k. And the last one is 4 over k. And so then what we remember is that the sum of all the probabilities has to be 1. So that would be adding those all together. That is 1 over k plus 2 over k plus 3 over k plus 4 over k equals 1. And that might look intimidating at first, but remember, this is just addition of fractions. And if you're going to add fractions, you need a common denominator, and we already have that. So actually, this is going to be pretty easy. So 4 plus 3 is 7. Plus 2 is 9, plus 1 is 10. So this simplifies to 10 over k equals 1. Multiply both sides by k, and you get that 10 equals k. And so what that allows us to do is go back in and write the probabilities. So that's 1/10, and that's 2/10, which, yes, I get. You can simplify that, but we don't actually have to yet. And that's 3/10, and that's 4/10. And they ask, what's the value of k? K is 10. We just figured that out. So that's fine. Now we're asked for the expected value. In order to do that, it's the exact same thing as the previous question. So why don't you pause the video and try this one? I think you'll get this one right for sure. Okay, what we're going to do, we're going to take each outcome, multiply by its probability. So 1 times a tenth plus 2 times 2 tenths plus 3 times 3 tenths and 4 times 4 tenths. And we're going to add all those together and simplify. So that would be 1 tenth plus 4 tenths plus 9 plus 16 over 10. And we could probably add those up in our head. I think 16 plus 9 is 25 plus another 5. That's 30 over 10, which is 3. And guys, that's going to be it for today. Okay, it's just discrete random variable tables, how to find them, how to make them out of a tree diagram, and how to find missing probabilities. Hope you enjoyed the video. I hope it was helpful, and we'll see you next time.